Hello. Uh, Last class we have discussed pushdown automata, and in this class we'll discuss deterministic pushdown automata or DPDA, deterministic pushdown automata or DPDA. So any pushdown automata is deterministic if there is never a choice of moves in any situation. The choices are basically two kind. If suppose del q a and x contains more than on pair, contains more than on pair, then surely this PDA is a non-deterministic nature, because we choose among this pair when deciding on the next move. So if it contains more than one pair, then obviously it is a non-deterministic pushdown automata. PD non-deterministic or in non-deterministic pushdown automata. However, if del q a x is always a singleton, we could still have a choice. Is suppose always if this always a singleton, in this situation we could still have a choice between using a real input symbol or making a move with the uh, epsilon or without reading a symbol. So thus we define, that means if there is a always a singleton move, if we obtain there is a single moves or singleton set are the outcome of this, then obviously there is a choice. That means whether you read a real input or making a move by using the epsilon transition. Thus we define a PDA or pushdown automata P is equal to Q sigma del Q naught Z naught F be a deterministic pushdown automata or DPDA if and only if the following conditions are met. What are the following conditions? Condition number 1, del q a x, where q is the state, is the input and x is a push down symbol, has at most one member from any q belongs to q. Has at most one member, that means singleton, from any q belongs to q, and a obviously belongs to the input alphabet, or a is equal to epsilon. That means a belongs to epsilon input or a belongs to epsilon, and x belongs to the push down stored symbols or PDA, push down stored PDS symbol, that is x. And number 2 condition, if del q a x is non-empty, is non-empty for some A belongs to sigma, then del q epsilon x must be empty. So these are the two conditions. If satisfied, then we say that it is a deterministic pushdown automata. So now the rules 1 says, what is the rule 1 says? Rule 1 says that for a given input symbol and any stack top symbol, at most on move can be made. So this rule 1 said for any given input symbol and any stack top, at most on move can be made. And number 2 condition says when null move is available, this basically when null or epsilon move is available, no input consuming alternative is available. Now we can explain. So rule 1 is simple. It has at most on member, and this A either it is a epsilon or it can be A equal to any input alphabet, or A can be epsilon and X can be any symbol on the PDS or push down store. But case number 2 or condition number 2 means suppose we have a transition like this Q naught A, and we have obtained this. Suppose it gives suppose the Q naught and A. What does it mean? It means you are in Q naught state and your present input is small a and stack top symbol is A. At that time you remain in the same state Q naught, and this A stack top symbol will be replaced by AA. Okay. Now if there is another move and there is another move like this Q naught null or A, which is also like this, suppose Q1 A, it means you are in the same Q1 naught state without reading any symbol. At that time stack top symbol is A. You can move any state which is Q1, and just this A will be replaced by A. So in this situation, what actually happened, if we draw the diagram, transition diagram, it will be look like this: Q naught, and here it is a Q1. The move is A will be replaced by AA or null AA. If this happens, then obviously it is not a deterministic pushdown automata. So condition 2 says if QAX is a non-empty for some A, this, then delta, when the string is exhausted, delta or the epsilon x must be empty. It must be empty. That means if this transition is available, this transition should not be available, or if this transition is available, then this should not be available. So when null move is available, no input consuming alternative is available. That means you may read A or may not, it means you may read A or you may not read symbol, but other are same. Stack top symbol is same. You are in the present state, that is Q naught. So if this present in a pushdown automata, then obviously it will be a non-deterministic pushdown automata. If this is not present, then obviously it is a deterministic pushdown automata. For example, suppose consider a language Example, suppose language is this n 1 to the power n such that n greater than or equal to 1. So now we want to construct a push down automata, deterministic push down automata for this language. So it means language is of the form 0 1 0 0 1 1 0 0 0 1 1 1, right? So now we can draw like this. Suppose your initial state is q naught, and when first 0 comes, so this should be accepted, 0 1 should be accepted, right? So when first 0 comes and your stack top symbol is z naught, suppose your present input is 0 and stack top symbol is z naught, and it will be replaced by 0 z naught. And when 1 comes, and your stack top symbol is 0, just replace this by null or remove this. Then you reach to state q1 and your string is exhausted because we have discussed for the string 0 1, and when string is exhausted, that means null, but at that time your stack top symbol is g naught and it will be replaced by g naught, and you have reached from final state, which is suppose q2. Okay, now what happen if the your string is 0 0 1 1? That means all the 0 should be pushed onto the stack first, z naught. So first 0 we have pushed by using this 0 z naught and 0 z naught will be this. And when 0 0, so when your input is 0, second input is 0, so you at that time stack top symbol is also 0, so now it will be just replaced by 0 0. Now by using this, any number of 0 you can push onto the stack. Now when the first 1 comes, you just move this, you just use this transition 1 then 0. That means your input is 1, your stack top symbol is 0, just replace this by empty, null, and you reach to q1 state. And in q1 state again your input is this 1, and at that time stack top symbol is 0, so you can make a transition like this 0, where input is 1, stack top is 0, just replace by this null. So by using this loop here, we can count the same number of 0 followed by same number of 1. So now it will be replaced by null, and string is exhausted, and that means string is exhausted. At that time your topmost symbol of the stack PDS is z naught, so just replace this z naught by z naught and you reach to the final state, which is q2. So as we have seen that the conditions, first condition and the second condition, look, first condition, it says that for any, look here, del q a comma x has at most one member from any q belongs to q. That means here this, for any transitions, only one state is there. And condition number 2, when null move is available, no alternative input consuming is available. So it is a deterministic push down automata or DPDA. Both the conditions are satisfied by this push down automata. That's why we call it as a deterministic push down automata. Now we discuss non-deterministic push down automata. So now non-deterministic push down automata or NP or ND, non-deterministic, or NPDA also, non-deterministic push down automata. Here all the symbols, as we have mentioned, or the meaning as same in case of deterministic push down automata, with only difference is the transition function. Now the transition function, this delta of non-deterministic push down automata is defined as Q cross sigma union null and push down symbols gamma to 2 to the power Q cross gamma star. That means it is a set. More than one pair will be there. Okay. So now application, we can say application is basically non-deterministic push down automata accept non-deterministic push down automata accepts set of all palindroms over suppose AB or 0 1 whatever may be. An example of this non-deterministic push down automata we can give in terms of transition function. We can give in terms of the transition function del, suppose Q1, it is Q1, so Q1 suppose A and this. It means your present input is A and stack top symbol is B and your present state is Q1. Now the configuration is like that, Q2 CD or suppose Q3 and it is replaced by null. So there is a two pair, right? That means from Q1 state reading a symbol A and if topmost symbol is B, you have choice. You can move Q2 or you can move Q3. But if Q2, then this B will be replaced by CD, or if you move Q3, then it will be replaced by null. That means we just remove this B from the stack top, right? So that's why it is called the non-deterministic push down automata. We have a pair here. Okay. Now we discuss the deterministic context-free language. Deterministic context-free language or DCFL, deterministic context-free language. A language we can define in this way: a language L is said to be a deterministic context-free language if and only if there exists a deterministic push down automata M such that L is a language that is M accepted by the machine M, deterministic push down automata M. Now the language, for example, now the language L a to the power n, b to the power n such that n greater than or equal to 0 is a deterministic context free language. Honestly, we can design it. We can find a deterministic push down automata for this context free language, right? So obviously the string are accepted by this is epsilon, then AB, AA, BB and so on. So we can design in that way. Look, if initial state is the final state, then only epsilon is accepted. Now when A comes, when your input is A and stack top symbol is G0, so just replace this by A G0. and you are in Q1 state, and in Q1 state more A comes, suppose A comes and A is the stack top symbol at that time, so it will be replaced by AA. In this way we push all the A onto the stack. Now when B comes and at that time stack top is A, just replaced by this null, and you have reached here, which is a state Q2. Now when again B comes and stack top is A, replace this by null. In this way all the B are exhausted, and that means same number of A followed by same number of B will be there, and the string ultimately will be exhausted. So here when string is exhausted, that is null, and at the stack top symbol is suppose G0, so just it will be replaced by G0 and you reach to the final state. So it is a, look here all the transition gives a single return. Now it is a, so it is a deterministic pushdown automata, and the language is a deterministic context free language, because we find a deterministic pushdown automata for this language L. Now if we draw, for example, suppose if we draw like this, instead of drawing this, if we draw this, suppose it is a Q0, and when A comes, stack top is G0, just replaced by A, Z0, and when A comes, just push onto the AA. Now when B comes and stack top is A, replace this by null. So in this way we can also accept this language. That means suppose epsilon AB, then AABB and so on, because suppose we have taken this string AABB, so when stack top is Z0 and A comes, so it will be AG0, so AG0 will be there, and when A comes, it will be on the stack top. Now when B comes, just remove this, when again second B comes, remove this, and in this way string is exhausted. So once the string is exhausted and stack top is G0, just replace the G0 and you will reach to some state which is a final state, right? But what happened, whether it is a DPDA or NPDA, obviously it violates the condition of the deterministic pushdown automata, because when null move, that is this null moves, when null move is available, no alternative input consuming should be available. Look here stack top is G0, stack top is Z0, here your input is A, here null input, that means you have a choice. When your input is A, you may read this symbol A or you may not read the symbol, so there is a choice. So it basically creates an ambiguity. So this is basically a non-deterministic pushdown automata. So if we draw the diagram like this, it will be a non-deterministic pushdown, or we can write simply non-deterministic pushdown automata, because of this and this. Now we try to design a pushdown automata for a context free language. Pushdown automata for context free language. Okay, so we know the grammar, that is, suppose or let G be a grammar having the tuple Vn, sigma, P and S, and also we assume that M is a pushdown automata where it is Q, sigma, gamma, del, Q0, G0, and F be a PDA or pushdown automata, right? Where this gamma, we know it is a Vn union sigma or union special symbol G naught. And G naught does not belongs to Vn union sigma. So G naught does not belongs to Vn union sigma. Now the steps to construct a pushdown automata from grammar G. So now the steps are: number one, the initial move to place the start symbol into the stack, and the pushdown automata moves to Q1 state. That means we can write in that way. For the initial move, it will be, suppose you are in Q0 and without reading any symbol, and at that time stack top symbol is G0. So it will move to some state Q1 and S G0 will be this. Here this is basically the start symbol of the grammar. Start symbol of the grammar G. Right? So this will be the initial move. And number two, the final move to accept, or for the accepting state, we say that it is a Q2. Q2 is the accepting state from Q1. Okay, where the stack is empty except G0. Clear? That means also we can in that say the string here the stack is empty. That means except the, we can say the stack topmost symbol is this, or we can be, or it can be written in that way, G0. So again I repeat, for the step 2, the final state move to the accepting state, that is Q2 from Q1, where the stack is empty except G0. And all other cases, otherwise the move of M, otherwise the moves of M as follows. For every variable, that is we can say A belongs to Vn, we have a move like this: Q1 without reading any symbol A, it will be like this, Q1 alpha, such that A to alpha is in the production P of the grammar G. For variable, we have to make this move. And B, for all A, that is terminal, for all A belongs to input alphabet, the moves will be tail Q1 A comma A will be Q1 epsilon or null. So these are the 3 steps to follow to construct a pushdown automata from a grammar G. Now we'll give an example. So now this is the example. Suppose we have a grammar G whose productions are of that form: S to ASA or BSB or small c. So first we have to, there is initial move to push this start symbol onto the stack. So the move will be, so this is the initial state Q0. So initial move will be to Q1. From here the moves will be without reading any symbol, stack top is Z0, just it will be replaced by S Z0. That means S is start symbol is pushed onto the stack. Now for all the variables, here actually S is the variable, but we have different alpha, that is alpha 1, we can say it is alpha 2, it is alpha 3. So for all of this, we have to make transitions like this. Epsilon is ASA or epsilon is BS SB and epsilon is small c. Okay, this is for the condition. This is for the condition or the step 3a, right? And for all the terminals here, 3 terminals are there: a, small b, and c. We have to make transition of this form. A will be replaced by null, B will be replaced by null, C will be replaced by null. Now step 3 is complete. Now final state move from Q1 to Q2. It is a Q2 state, and it will be only epsilon, that is string is exhausted, stack top is G0, and replaced by this and reach to the final state Q2. Clear? Now this is the pushdown automata. Obviously it is a non-deterministic pushdown automata in NPDA, and it is the corresponding pushdown automata for the grammar G. This is the grammar, suppose this. Now we'll give a step-by-step process how it basically accept the language generated by this grammars. Obviously we know the language that is generated by this grammar is, it will be only C or A, C, A, or B, C, B, or A, B, C, B, A. This kind of language are basically generated by this grammar. Now we'll take this language A, B, C, B, A for the sequence of moves, right? So consider this A, B, C, B, A string, right? We consider this a string. Now what will be the sequence of moves? So initial move will be Q0, and your string is A, B, C, B, A, and your stack top symbol at that time is Z0. Now one step move, it will go to Q1, and all the things will remain same: A, B, C, B, A, and we have to push the start symbol onto the stack. We have done this. Next move will be Q1, as first symbol is A. So now this S will be replaced by which of the production rule? A is A. So A, B, C, B, A. Now this S will be replaced by A, S, A, G0. Right? Now when your input is A, stack top symbol is A, it will go for A will be replaced by null, and it will remain in the same state. So Q1, now B, C, B, A, and S, A, G0. Now go to here. Now next move will be Q1, as first symbol is B, so B, C, B, A, and this S will be replaced by B, S, B, B, S, B, and G0. Sorry, B, S, B, and A also there. A is also there. Now A and G0. Right? Now this B, as when B is your present input and stack top is B, replace this by null. So it will be Q1, now C, B, A, and S, B, A, G0. Now next move will be, when your input is C, stack top is S, just replace by this Q1, CBA, this S will be replaced by small c. CBA and G naught. Now, when C comes, stack top is C replaced by this null. So it will be Q1, BA, BA, G naught. Again, when B comes, stack top is B replaced by this null. So it will be Q1, A, G naught. When A comes, stack top A is present input and E is the stack top replaced by this null. It will be Q1, string is exhausted, and this. Now when this is the configuration, or these are basically same, you can also write this. Okay, so now string is exhausted, stack top is G0, just reach to the final state where it will be Q2 and your string is exhausted and it just it will be G0. So these are the sequence of moves for the this push down automata which we have generated for the context free grammar G. So thank you.